Section 3.2, Graphs of Functions. Our objectives are to determine if a graph is a function and to analyze graphs to determine domain and range, maxima and minima, inflection points, and the intervals where they are increasing, decreasing, concave up, and concave down. So we've already talked about functions before and what makes something a function. So we've also done this first graph before. So I would, if I were you guys, pause the video and see if you can do this on your own, and then you can check your answers. So for the first one, f of 0, this means that we want to find the y value when we have an x value of 0. So if I look on my graph, when I have an x value of 0, notice right here I get my y value of 8. So then for f of 3, we're doing the same thing. I want to find the y value when I have an x value of 3 on my graph. So the y value for an x value of 3 is 1, so that would be my answer here. For C, now I want to find the domain. So notice that we have an arrow on the end of our graph right here. So I know that my x values are going to continue to go down. So if I go all the way up to an x value of 1, we have some problems because we have an open circle here and an open circle here. Now that line that's going down on your paper is just from my computer program, so you can just ignore that dotted line. So then at x value of -1, it goes all the way up to now 7 here. And again, it's an open circle, so I'm going to leave that there. So now I just have to put this in interval notation. So parenthesis, -infinity, comma, 1, parenthesis, union, parenthesis, 1, 2, 7, parenthesis, and again, because we're not including those points since it has open circles, and again, you don't include -infinity. So then for our range values, remember those are our y values that we are now looking at. So notice that again our graph goes down to -infinity and it comes up to a y value of -1. At a y value of -1, it's taken care of here. So if you also look at a y value of 5, that open circle that we have right here is taken care of with a y value of 5 here. The open circle that we have right here is taken care of with this y value. So that means that I'm stopping all the way up here at a y value of 8 and going all the way down to -infinity. So of course I have to write this in order, parentheses, -infinity to 8, and we're including 8, so now it would be a bracket. So now for this next part, it says, example, find the domain and range of the function. So what you all will have to do on your homework for these notes is you're going to have to do this on your own, and then we will go through and check these answers tomorrow. So I'm going to go ahead and skip to the next part. So the vertical line test. So a graph in a coordinate plane represents a function if and only if no vertical line intersects the graph in more than one place. So if we want to determine whether or not something's a function, we're going to use our vertical line test, or sometimes it's called the pencil test, to determine this. So I have my vertical line right here. So what I'm going to do is see if this graph right here for A passes the vertical line test. Notice that pretty much everywhere we hit on the graph, it's hitting in more than one place. So because it hits in more than one place for each of these x values, so each x value has two output or two y values, because it hits here and here, we know that for A, this is not a function. And you should hopefully remember this from Algebra 2. So what I want you all to do for your homework is do the same thing for B, C, and D, and tomorrow in class we will go ahead and talk about those. So for part 3, we're going to talk about analyzing graphs. We're going to talk about x and y intercepts, intervals where they're increasing or decreasing, maximum and minimum, and intervals where the graph is concave up or concave down, points of inflection as well. So intercepts, hopefully you remember from Algebra 2. How do you find the x-intercept for something? You're plugging in 0 for y and then solving for x. And for the y-intercept, you're plugging 0 in for x, then you're solving for y. And of course, just plugging it into the original equation that you were given. So I'm going to go to the next page. So increasing and decreasing functions. this can be a little bit tricky, so we'll have to make sure you're paying attention. So increasing on an interval if the graph is always rising as you move from left to right. Decreasing on an interval if the graph falls as you move from left to right. So again, you're always going from left to right on your graph as you're doing this. Constant if a horizontal line over the interval that you have, so any horizontal lines are constants. And we use x values for the intervals when we're writing them out. So we write it in interval notation. So some students get confused because they think they're writing the domain, but really we're just writing the intervals for increasing, decreasing, constant. So it's really important when you write these intervals that you make sure you write if it's increasing, decreasing, or if it's constant. Otherwise, you would get it confused with the domain or is it the range. So always do that. So if we look at this first graph that we have here, it kind of looks like a parabola. So remember that the key for this is that we want to look at this graph as it moves from left to right at what's happening. So I'm going to get myself a line here to kind of show you. So if I have this line here, as I'm moving from left to right on my graph, we're looking for these intervals where we're increasing, decreasing, or constant. So as I move from the left side and then I get to about this point right here, notice that my y values as x is increasing, the y values seem to be decreasing. So we would say that it's decreasing, and we would use the interval from negative infinity to, and you have to look at now your x value. So what's the x value here that we're stopping at? Negative 7. And notice that I'm going to use parentheses for this because that point at x equals negative 7 is the place where your graph is changing. So since our graph is changing, we neither say that the point is increasing nor is it decreasing at that point. So that's why we're going to use the parentheses because technically we're not really going to include it. So then the next part we're going to look at is if we keep going from that point on, here. So if we keep going, notice that from that point on, our y values as x is increasing, y is increasing. So then we're going to say that we're increasing from negative 7 to infinity. So that would be what I would write for this problem if it asked me to write the intervals for whether or not we're increasing, decreasing, or constant. And notice there is no horizontal lines as a part of this graph. And so since there are no horizontal lines as part of this graph, that's why we do not have a constant. So now if I go to the second graph here, looking as we move from left to right on our graph, as our x values are increasing, what are our y values doing? So notice that as we do that, our y values seem to be increasing and there's no place where it seems to change at all. So I would say that this entire graph is increasing on the interval from negative infinity to infinity. Now, let's say my graph had been going the other way and it was going up this way and then down this way, then if I had a graph like that, it would be decreasing over the entire interval from negative infinity to infinity for that one. So then the last graph, as we move from left to right on my graph, notice that I have a horizontal line, which means that I have a constant graph because my values of x here, as I go from left to right, the y values are neither increasing nor decreasing, so it's constant from the x values to negative infinity to positive infinity. So again, the key is to remember you're always using your x values for increasing, decreasing, or constant, and that when you're going from decreasing to increasing or vice versa, you always use parentheses. For constant, you would normally use brackets to include the point. However, whenever we're working with infinity, we know that we use parentheses because we're not really including the point. So for example 4, it says on what interval is the function f of x equals the absolute value of x plus the absolute value of x minus 2, increasing, decreasing, or constant. So we're going to do the same thing that we did for the other example. So I'm going to take my line here and I'm going to go from left to right of my graph. So as my x values are increasing, my y values, you'll notice, are starting to decrease until we get here. So I'm going to write, and yes, I have to write decreasing. So we are decreasing from the interval then from x values that come from negative infinity and stop at an x value of 0. And of course, again, I'm not going to use bracket there because that's the point at which it's changing. So then notice from the next part, from 0 as an x value to an x value of 2, we are a constant. So for constants, because it's constant from the x value of 0 all the way to the x value of 2, this is the only one that we actually use brackets for. So I would say bracket 0 to bracket, or to bracket. And that would be my constant interval. So then for the last part, notice that as we keep moving from left to right in my graph, as my x values are increasing, my y values are also increasing. So that means the last part of my graph is increasing on the interval from parenthesis 2 to infinity. And again, we're using a parenthesis at 2 because at that point, it's neither increasing nor decreasing. So that's it for this page. So let's go to the next one. So now it says, is the graph increasing, decreasing, or constant? Find the domain and range. So for these graphs right here, I want you all to do this on your own. So I want you to challenge yourself, and then what we'll do in class is we'll look at the domain and range and if it's increasing or constant. So do that on your own. So the next part we're going to talk about is local maximum and minimum points. So for these are the peaks and valleys of the function, of the graph that we have for the function. And they're the turning points for which the graph shifts from increasing to decreasing or vice versa. So that's the points of inflections are the turning points. So I'm going to write a note there. Those are the turning points. So a function has a local maximum if at the graph, all the points around it are lower, the y values are lower than that point. So right here, this is a maximum point. This is a maximum point. So both of these are maximum. And we have minimum points here and here because those are the lowest points relative to the points around them. So the maximum are called the peaks. The minimums are usually called the valleys. So for these points that are maximum minimums, notice that our graph on this end for the maximum keeps going to infinity. So these points that we have are usually referred to as relative maximum points, because relative to the points around them, they're a maximum. However, because our graph, again, right here goes to infinity, we know that it's not the actual highest point on our graph. So then the other points for the minimums down here, these would be called a relative minimum, because relative to the points around them, they are the lowest. However, notice that the graph right here keeps going on to infinity, so it's not the actual lowest value of our graph. So if we also have what's called an absolute maximum or an absolute minimum. And so if you think about a parabola, this point on my parabola where we have our vertex is the actual lowest point on our graph. So this would be called an absolute minimum, because there is no other lower part of your graph that we have. So let's go ahead and go to the next page. So on this next page, you actually have the graphs here. So I'm going to pause the video for a second so that I can graph them in. Okay, so before we do that, I didn't realize there was the next part to the page, so I'm going to scroll down from where we were before. So for example number 5, it says find all the local maximum and minimum increasing and decreasing intervals, and we want to find the x and y intercepts. So if we're looking at these equations, if we want to find the local max and minimum, increasing and decreasing intervals and x and y intercepts, we can go ahead and use our graphing calculator to help us. So while I'm getting my graphing calculator started, you all should also be getting your graphing calculators out to do these problems with us. So in my graphing calculator, of course, if we're analyzing this function, we're going to want to first plug in the equation into our graphing calculator. So we have in our y equals on our graph negative x cubed plus x. So now that I have this in there, I'm going to go ahead and hit the graph to see what it looks like. And usually, if you don't have a good viewing window, you can hit zoom 6, and that kind of gives you a nice little window to look at. So for this graph, I have to find a few different things. So I usually like to start by finding my maximum and minimum points. So in order to find your maximum and minimum points, you can use your calculator second trace button. Oops. So if we do that second trace, I'm going to find the minimum first. So use your left and right arrows, and you can notice it looks like to the left of that we have our minimum. So the left bound means we want to pick something on the left side of that, enter, and then pick something to the right of that, but trying to stay as close as you can, enter. And then when it says guess, all you have to do is hit enter on your calculator. So here we have our minimum. So I'm going to write this down. So we have a minimum. And of course, this is a relative minimum because it's the minimum relative to the points around it. So the relative minimum, I'm going to round 4 decimal places, so negative 5.774, or no, sorry, negative 0.5774. Comma, and since this is a minimum point, I'm going to actually write the y coordinate as well. So negative 0.3849. And then for the next part, we want to find the maximum since it looks like we have a maximum to the right of that. So second trace, maximum. So for that, I'm going to have to, it says left bound, so I want something to the left of where I think the maximum is. So somewhere around here, enter, and to the right of where I think the maximum is. It doesn't have to be these exact points that I use, just as long as it's close, enter, and then enter on guess. And the maximum that I get is again a relative max relative to the points around it. So for this, of course, I'm going to write the x and y coordinate point since it's a maximum point. So after you find the maximum and minimum points, now it becomes a little bit easier to find the intervals where we're increasing and decreasing because you're basically using your maximum and minimum points for that. So I know that my graph from here all the way to about right there where the minimum is. Notice as we move from left to right, what are our y values doing? They are decreasing. So for the first part of my graph, I'm decreasing on the interval. And again, don't forget you're using your x values, so negative infinity to the x value of my minimum point, so negative 0.5774. Whoops. Okay, so I just made it a little bit larger to look at. So we're decreasing from our x values all the way going to right here, which would be our minimum value, our minimum point. So then we need to figure out what's happening in between here to here. So on that space, which is from my minimum x value to my maximum x value, notice I'm increasing. So I'm increasing from negative 0.5744 to the x value of my maximum, which is 0.5773. And then from that maximum point all the way down here in my graph, notice that as my x values get larger, my y values are decreasing. So in this case, now I again am decreasing from 0.5773, because that's the x coordinate of my maximum point, to positive infinity. So then the next thing we want to find is our intercepts, so our x-intercept and our y-intercept. So for the x-intercepts, we can use our calculator to help us find them. So on your calculator, if you hit second trace, and notice you have the 0 button there, number 2, we can use that to help us find the zeros. So I'm going to scroll over to the first one. And so here is where on my graph I think I have my 0. So in order to find the 0 using this, I need to pick something to the left of this point where I think it's 0. Something to the left would be up here above, something to the right would be below, and then hit enter. So above, left, enter, below would be right, enter, and then we'll guess the points in between that. So notice I get a 0 of -1, so that means that's one of my x-intercepts, so I'm going to write x equals -1. Now I just have to go ahead and find the other two, so I'm going to do it again. Second trace, 0. It looks like it's somewhere in between, so enter for left bound. Now I need something above. Enter, because it looks like we have one at 0, 0. I'm just checking to make sure, which we do. So I have another x-intercept of 0, and then it looks like we have another one to the right of that. So second trace 0, which is number 2, and I'm going to scroll over. So something to the left of where that 0 is would be somewhere right there. Something to the right, the 0 would have to be below the x-axis. Enter, guess, enter. And we get an x value of 1. Now, if that's hard for you to see on your graph, you can always hit zoom and zoom in, and then hit enter. I notice that you can kind of get a better view for what's happening at the graph. So that's why we said before this was our minimum value, this is our maximum value. I knew the values were decreasing till I got to here, and then the next part they were increasing to here and decreasing to here. This was my first intercept, the next one, and then the next one here. So now the next part we need to find our y-intercept. Obviously this one's easy to see because we already found the 0 and we saw that the y-intercept is going to also be 0 because we had the point 0, 0. So if you didn't know that, you can always go to second trace and number 1 value. And this lets you put in any x value you want to figure out what it is on the graph. So as long as you're looking at that on your graph. So if I hit 0, enter, notice I get 0, 0. So I know I have a y-intercept of 0. And then the last part of this, we wanted to find our domain and our range. So for our domain, I'm going to go ahead and go back to my graph and just zoom out. So zoom 6 to go back to my standard window. Now, I can look at the graph for this, but however, remember in the last section, we were using algebra to help us to determine the domain. So remember for this graph, I do not have any of my restrictions that I have to worry about. So our graph was originally y equals, or f of x equals negative x cubed plus x. So do I have any variables in my denominator? No. Do I have any variables underneath a radical? No. Therefore, my domain is going to be all real numbers. And then my range, if I don't have to worry about anything that I'm plugging into my graph, then that means I don't have to worry about anything that I'm getting out of my graph for my y values. So my range is also from negative infinity to infinity. And this is basically almost the whole analysis of our graph. We still have to talk about concavity, which we'll do on another time. So what I want you all to do now that we have all of this is I want you to practice doing the next part of your notes. So you can go ahead and do this equation on your own. So find the local max and min, increasing and decreasing intervals, your x and y intercepts, and I would also practice finding the domain and range for that as well. And then tomorrow in class, what we'll do is we'll talk about the concavity inflection points and any questions that you have, and we'll also go over those other problems that we saw.